1/3 to the 6th power over 1 minus 1/3 using my formula, all minus 1, and as far as I'm concerned, I have an answer. I could do some simplification, but there's really no reason to. That is a number. I'm done. So there's a whole bunch in the back, right? Every section has practice problems in the back, in chapter 15 or something, with practice. So there's a bunch of geometric series in the back to practice with. Yeah, what you got, AJ?
Oh, where did the 6 come from? On the bottom?
Right here?
Yeah, where did that 6 come
I'm using this formula, which says if you're summing from 0 to some number, it's 1 minus whatever your r is to the n plus 1 problem.
Oh, so you
And so it started to go into 5, so 5 plus 1 is 6. Others?
Would you need to check that before you could distinguish which one you need to use? To check to see if it's convergent or divergent?
No, because this is a finite sum.
Oh,
I'm adding up finitely many numbers. I know it converges.
I didn't think that.
Right? Even if this was 5 million, I could change this whole problem. Mess with the photography here. Nothing changes except that. Right? And it's still a number. There's 500 terms. You add up 500 numbers, you get a number. It's a smaller number. I mean, it's a bigger number. Why? Because when you raise 1/3 to the 501, it's much smaller than 1/3 to the 6th. And so you're subtracting off something smaller. That makes your numerator bigger. That makes the whole thing bigger. So it doesn't look like it gets bigger, but it does when you add up the additional 496 terms. 494 terms, whatever. Okay? Good? All right? So if I had the sum from n equals 0 to n equals 4 to infinity, 1 over e to the negative n, what would you do with that one? Hmm? How do you want me to break it up? I'm confused. Tell me what to write.
E to the -1 times e to the n. So that way you can.
I think that's e to the -1 plus n, which is e to the n minus 1, which I don't think is equal to e to the negative n. Not equal to that. Good idea, though. Live dangerous.
Could you do it like the inverse of it, like e to get like 1 over e to the n.
Okay, that's the sum from n equals 4. When in doubt, write something you know is true. Okay?
Which is e to the n. Yeah.
Which is what? R would be E. Now what?
Now you subtract.
Subtract off the 4 terms?
Make it go to 0.
Okay, we can do that. So now you want to make it sum n equals 0 to infinity of e to the n minus e to the 0 minus e to the 1 minus e to the 2 minus e to the 3. Is that right? Because then it will start with e to the 4th. Okay. Now what?
1 over 1 minus e.
Formula is what?
1 minus e.
Are we done? I got news for you. Brandy's not going to give you much credit for that problem. Why not?
No definite answer.
What's wrong?
E is greater than 1.
E is greater than 1. What's E equal to? About 2.71782819. dot, 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 right? Which means this one doesn't exist, and this one doesn't exist, and this one doesn't exist. None of these exist, right? Because you can't apply the formula because E is bigger than 1. So right here, alarm should have gone off. Police car sirens. R is greater than 1. It diverges, right? R is bigger than 1, so you know it diverges. Okay, I think you know how to manipulate them. I think you know how to work with the basic algebra of them. That's geometric series. So, Andy?
I'm sorry, why does R have to be greater than 1?
R has to be absolute value of R has to be less than 1, and it's really not as complicated as it seems. What's the definition? The sum from n equals 0 to infinity of R to the n is by definition the limit of the partial sums. Right? The definition of an infinite series doesn't make sense to add up infinitely many numbers. So the definition of this sum of infinitely many numbers means you take the limit of the partial sums, right? We did a bunch of partial sums early on. Add up the first term, add up the first 2 terms, add up the first 3 terms, add up the first 4 terms, and see what that goes to, right? Okay, well if you believe this formula, which we did enough problems in class, then I kind of derived it, but we did enough problems to, this is the partial sums, right? So this is the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. With me so far, Andrew? Mm-hmm. Right? All I did was write it out as the partial sums. And if we believe this formula, might not, but if we believe this formula, which I did give you one of the rare examples of actually gave you proof of something, then now, when will this limit exist? If this number is bigger than 1, what's going to happen to the limit of, if R was equal to 2, what's the limit as n goes to infinity of 2 to the n plus 1? Well, it's going to get bigger and bigger and bigger really fast, isn't it? 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the millionth. So the top's going to blow up unless R is less than 1. Right? So if R is less than 1, you're taking a half. If R is less than 1, say R equals a half, then the limit as n goes to infinity of R to the n plus 1 is the limit as n goes to infinity of 1/2 to the n plus 1. Well, that gets smaller and smaller and smaller as n goes to infinity. So this part goes to 0 if the absolute value is less than 1. And when it goes to 0, what do you have? You have this formula. So you really only have to remember this formula, since you've got to remember both, and the fact that the definition of the infinite sum is the limit of the partial sums. So if you understand those two basic important ideas, that the infinite sum means the limit of the partial sums, and that if R is less than 1, this thing goes to 0, then you've got your other formula. And that's why it's got to be less than 1. Good? Other questions, anything up there?
So if it's greater than 1, it diverges?
The infinite sum, if it's greater than 1, it diverges. That's correct. And the bad news is you can plug something in there and get an answer. It just doesn't make any, it's just wrong.
Right. This
formula is only valid. The formula is only valid when R is less than 1. And if R is bigger than 1, it diverges because of this argument, right? If you want to know what it is, suppose R is bigger than 1. It's this, which is this, and this goes to 0 if R is less than 1. It goes to infinity If r is bigger than 1, well, let's start with the absolute value, not confuse things. If r is bigger than 1, this thing goes to infinity. Right, if r is negative and bigger than 1, then you got to worry because it's even odd, right? It's it's messier. And if r is equal to 1, you're going to get 1 every time, right? So you're going to have 0, but that doesn't make sense. Because you know if you add up 1 over and over and over again, you're not going to get 0. Alright? So if r is equal to 1, you know it doesn't make sense. So that's why it's got to be absolutely less than 1 for this formula to make sense.
Okay.
Good?
Yes, sir.
Good questions? You good? Okay, we'll try to show you where we're going now. So now what we have after all this couple of weeks of work on series is we have one kind of series that we can figure out, geometric. And hopefully we have an understanding of what a series is, this infinite sum, which really is a limit of partial sums. And I'm willing to give up 2 weeks on that introductory concept just so that we understand what a series really is. It's a sequence of the partial sums. So now, where we're going is twofold. We're going 2 places. What we're going to do now is most series, for this kind of series, we not only know when they add up, as Chris just pointed out. If the r is bigger than or equal to 1, this diverges. If it's less than 1, it converges, and we know what it is. We get an answer. That's never going to happen again. For all the rest of the series, basically, we're going to be able to say it either diverges or it converges. That's important enough to know because with computers nowadays, if you just know it converges, just add up the first gazillion terms in about a microsecond, and that's what it converges to. But if you add up the first gazillion terms of one that diverges, you get a number, and you assume that's what it converges to, and you're wrong, because it diverges. There's no amount of numbers you can add up. So for the rest of the series, so the rest of the story is, now we only hope to figure out if a series converges. And so we're just going to have a bunch of tests, about 4 or 5 tests. You look them up in any book and memorize them and just go, what test can I use on what series? Kind of like back in integration, it was, what technique do I use to try to integrate this one? Now, what most series tests look like is, here's 20 series, does it converge or not? Pick a test and try to figure it out. So where we're going is a bunch of tests. We'll talk about this one today, the integral test, the p-series test, what's often called the direct comparison test. I mean, obviously these are all in your notes. And then the limit comparison test. And there's a whole ton more. There's a root test, which I think I skipped. And then there's a ratio test. And then there's some others. So where we're going next is this collection of tests, which, I mean, I could just write them all on the board today and say, how do you use each one? Because each of them is pretty simple to implement, kind of like integration by parts. If I give you an integral and I say, use integration by parts, you're never going to miss it, right? I know the formula, I wrote it down on my 3x5 card, I'm a computer, I figure it out. These series tests are kind of the same way. If you could remember them all, and you wrote each one down, and I said, here's a series, apply the direct comparison test to it, you'd get it right. So the key is to understand which one do I try to use when, which one's going to work. That's what's going to be hard, just like with integration. And the other is to try to give you some intuition as to where these tests came from. So let's look at the integral test with a simple example like this one. So I'm going to try to introduce the integral test. Now what I'm going to do is I'm going to compare this series to the area under a certain function. So I'm going to graph this function. I'm going to look at what area is underneath it. So put 1 in, I get 1/3 out. Put 2 in, I get 1/6 out. Put 3 in, I get 1/9 out. 4 in, I get 1/12 out. So there's what 1/3x looks like. Now, take this series. I'm going to make it into a bunch of rectangles. What's the first term I get out of that series? 1/3. What's the area of that rectangle? 1/3, right? So that one has area 1/3. What's the second term I get out of there? 1/6. What's the area of this not to scale rectangle? I messed that one up, didn't I? No. Right? 1/6. And the third term. So now, how does, if I did that forevermore, what is the black shaded area in terms of integrals? The black shaded area. If I were to write that down as an integral, what would it be?
Integral from 1 to infinity.
I'm going to go on forever. It's shaded all the way out there.
From 1 to infinity.
Integral from 1 to infinity of 1/3x, right? How does it compare to the area? How does that compare to the area here and here and here? Going on forever. It's smaller, right? It's less than the sum from n equals 1 to infinity of 1/3n. That clear? With me, Dominique?
Not really.
No? Okay. You agree that the area of the first rectangle is 1/3? You with me there?
Is to make the black part after you say area.
Okay. So you're with me on the area of each of those, and it does add up to the same as this, right? 1/3 plus 1/6 plus 1/9 plus 1/12, right? So I made a bunch of boxes that if you added them all up, their area, it would equal to this, right? Okay. Then what I'm saying is, let's just look at the area under the curve. Remember on the last test, those improper integrals?
Yeah.
Infinite integrals, right? Unbounded area. From 1 to infinity, the area under the curve would just be integrate the function. 1/3x. So all I'm saying is, the area under the curve, isn't that less than the area of the boxes? Well, the area of the boxes is that sum. The area under the curve is that. So this is bigger than this. So if I could figure out that this was infinite, If I compute this integral and it turns out to be infinity, what does it mean about that sum? It diverges, right? Because it's bigger. Okay? Now I'm going to do something even a little bit tricky. Any questions there? Okay. I'm going to do something a little bit trickier now. I'm going to draw the same picture, I hope. Try to draw the same picture. Except I'm going to put the rectangles underneath it. Now, what's the area of this rectangle?
1/6.
1/6?
9.
1/9. Okay, so what do I have for the red this time? I have the sum from n equals 2, right? I just threw the first one out, right? Now, how does that compare to the area under the curve?
It's less.
Right, now it's less than the area from 1 to infinity of 1 over 3x dx. So if this were finite, if this were a finite number, what would that say about my series? It converges, right? Because it's got to be finite also. So if this guy were finite, then this one has to be finite too.
Could you take both of those areas and subtract them to get an accurate answer for the function?
Well,
seems like it would be pretty close.
keep in mind that if I know what this one is, if I compute what this is, and I get a number, all I know is that this is less than that. That doesn't tell us how close it is, right? But your idea is valid, because if I wanted to add, suppose I really don't want it from n equals 2 to infinity, do I? I really want it from n equals 1 to infinity, right? How could I make it from n equals 1 to infinity? What could I add to both sides?
Yeah, you subtract the first one.
Yeah, just add the first one back, right? If I added the first one back, this one would say n equals 1 to infinity of 1 over 3n would be less than integral from 1 to infinity of 1 over 3x dx. But I added that to that one, so I better add it to this side, right? Okay, so let's see what we've got here. Let's combine these two statements, and what we have is this. The integral from 1 to infinity of 1 over 3x dx is less than my sum from n equals 1 to infinity of 1 over 3n, which is less than the integral from 1 to infinity of 1 over 3x plus 1/3. Should put a dx in there. Did I combine those correctly? That this is less than that, that's what I've got there. And this is less than that, that's what I've got there. So that does tell you what you said. It's trapped between two numbers that differ by 1/3, right? So if I computed this number and it turned out to be a number, and I computed this one and it turned out to be a number, then I'd be within 1/3 of my answer here. I wouldn't know what it converged to, but I'd know it within 1/3. Okay, so let me say what we conclude here. If this is less than this, from this statement, I can conclude that if the integral from 1 to infinity of 1 over 3x dx diverges, then what's true? Then the sum from n equals 1 to infinity of 1 over 3n diverges. And over here, from this statement, I can conclude what? If the integral converges, then the sum. Well, that means that if I see that what's on the inside of the series is something that I can integrate, just integrate it and you know whether the series converges. Hence the name, the integral test. If you can integrate it, you know the answer. Yeah?
Shouldn't it be n equals 2 over here?
Should it be n equals, which one here? Well, remember that we started with this less than this, right? But by adding 1/3 to both of them, by adding the first term, if this is a number, then this plus 1/3 is a number. So this is still finite. So that's the good news is, Joseph, the good news is that that means I don't have to worry about where it starts. In fact, if this one started, if the one I had given you started at 5, just integrate from 5 to infinity of this. If it exists, it converges. If it doesn't exist, it diverges. Okay, so now I need to do the work. So let's do the work right quick. So now I'm just going to apply the integral test. See the right integral test. To the sum n equals 1 to infinity of 1 over 3n. Okay? Integral 1 to infinity 1 over 3n. Oops, x. Gotta change it to x's. We cannot integrate with n's. Mess us all up. Okay, here we go. I think it's the natural log of 3x with a third out front. Because if I took the derivative of that, I'd have 1 over 3x times the derivative of the inside, which would be 3. Oops. I'm cheating. Brandon never let you get away with that. Right? And I'll use the capital T for Ted. Well, I've got ends all over the place, so I'll... Right? That's... Yeah, an infinite integral means you've got to do a limit. Now, limit t goes to infinity. I integrate it. I get 1/3 natural log of 3x from 1 to t. I plug in t, I get the limit as t goes to infinity of 1/3 natural log of 3t minus 1/3 natural log of 3. I plug t, I plug 1 in, I subtract them, that's a number. But this, as t goes to infinity, the natural log goes to infinity.
Wouldn't it be 1/3 natural log of x?
That's what I thought too. Because you throw the 1/3 in
You
front.
took the 1/3 out, so you left the 1 over x.
We're both right, right? If I take the derivative of this, if y is 1/3 natural log of 3x, and I take the derivative, I get 1/3 times 1 over 3x times 3. Oh, you're right. I got one too many 3's, right? 1/3, 1 over 3x times 3, they cancel, and I get 1 over x. I failed. So, if I was going to do it my way, I need a 1/9 out there or something, right? We'll do it your way.
Good, I love the movie.
How's that? You happier now?
Better.
Thank you, Joseph. Yeah, the 1/3 comes out front, then it's 1/3 natural log of x. My way, I'd have to put a 9 out here, right, to get it right. Because then I'd have 1/9, 1 over 3x times 3. Oh, wait a minute. My way worked. My way
Your
worked.
3's cancel. Yeah. Your way works too, because the 3 cancels.
Yeah, we're both right. What I said originally was right. We're both right. That's odd. Have I lost my mind? See, if I take the derivative of this, I have 1/3. I put 1 over 3x. and I multiply that over the inside, which is 3. So I get 1 over 3x, which is what I want. And your way works as well. And why does that work?
Because on the top one you have 2 extra 3s, so they cancel each other out. And on just 1/3 natural log of x, keep your 1/3, and then the derivative of the natural log is just 1 over x. So
Yeah, see, it's just surprising that 1/3 natural log of x plus some constant is equal to 1/3 natural log of 3x, right?
Whenever you pull out the 1/3, how is there 3 remaining on the inside?
Well, what he's saying is, if you pull out the 1/3, that's what he's saying, right? He's saying if you pull out the 1/3, then you've got 1 over x.
Right.
What I'm saying is it's a little surprising because these answers look pretty darn different, right? You wouldn't expect, if 2 students got this on the test, and you were teaching this in high school, you'd think one of them had to be wrong. Wouldn't you? Because they don't look the same. Well, remember that it's plus k. So if you write it like this, you remember your algebra that says 1/3 natural log of x plus natural log of 3. So now what do you have? You have 1/3 natural log of x plus a constant 1/3 natural log of 3. So 1/3 natural log of x plus a constant can be the same as that as long as the constant is that. Pretty neat. Anyway, that's an aside. Either one of us, apparently Joseph and I can both integrate. That's the good news. So we'll stick with his, since his was simpler. 1/3 natural log of x. We plug them both in. Now the limit as t goes to infinity of the natural log of t, that goes to infinity, so this whole thing diverges, right? So this integral does not exist. So this series does not converge. The series diverges as well. So we conclude sum n equals 1 to infinity of 1 over 3n diverges by the integral test. Any questions on the steps we went through there? This really, if you made this a generic a to the n and drew these pictures with just an a, then you have the proof of the integral test. What I did here is essentially a proof of the integral test, but I used a very specific series. But if you just replace the 1 over 3x, what, if this was 1, what height would this be if I had a generic series? It'd be height A1, right?
Right.
So one of your problems asks you to prove the integral test. If you really understand this, you can probably do it.
Every time we use the integral test, do we need to draw the pictures and stuff?
No. The integral test, this was to help you understand why it makes, I mean, it sounds like magic, right? You have a series, you throw away this, you change it to an integral, and you integrate it. If you get a number, the series converges. If you don't get a number, the series diverges. That's crazy. Who would believe that? Well, you only believe it if... How many engineer? I'll take it. Other than any engineer, trust us mathematicians. But this picture shows you why it's true, right? The picture shows you why it's believable, because the series is very close in size to the integral, the area under the curve. It also shows you why we cared about integrating from 1 to infinity in the first place. Because these improper integrals are what tell us whether these series converge. Other questions? Now, I think you'll need to draw these pictures if you want to understand the next few problems. Like one asks you to do the harmonic series, which is the exact same series, but no 3 in front of it. One of them asks you to prove the integral test. So you need to understand the pictures and draw the pictures if you're working those problems. If you're just looking at a series that says, does this series converge, use the integral test, This is all anybody would do. Okay, let me kind of tell you what happens next. What you're going to discover soon is that the integral, depending on what this p is, converges or diverges. You're going to use, I should write this, it's one of your problems. Use the integral test to show that this series converges or diverges depending on the value of p. What was the value of p in our problem? 1, right? We had 1 over n to the first, right? Now, if I made it 1 over n squared, what would happen to my graph? If I did 1 over 3x squared, what would happen to the graph? Go up or down? It'd get smaller, wouldn't it? It would actually look like this. Because at 1, it would still be 1/3, right? Less than 1, the bottom gets bigger, so the bottom gets smaller, so the whole thing gets bigger. Bigger than 1, the bottom gets bigger, so the whole thing gets smaller. So 1 over, if this one had converged, we'd have known this one converged, right? Yeah, well, unfortunately, this one didn't converge. But there's a chance for 1 over 3x squared to converge, right? Because it's smaller than this one. Well, that's what you're going to figure out. You're going to do some integral tests to things like 1 over x squared and 1 over x to the 1/2, and you're going to figure out, well, what values of p make this converge? And we already know it diverges. We already know it diverges if p equals 1 based on what we just did. So you're going to figure out that if p is bigger than 1, this guy's going to converge. If p is less than 1, this guy's going to diverge. That's going to be our p-series test. So the p-series test is going to follow directly from the integral test. Then the direct comparison test is going to say things like this. Suppose I already knew suppose this guy converges. Actually, I think that's a girl. Suppose this girl converges. It's kind of hard to tell when you're writing math whether it's a guy or a girl. I'm pretty sure that one's a girl. If this one converges, if she converges, and I want to study this one, does it converge or diverge? Converge. Why?
Yeah, just a little bitty constant.
Yeah, it's a constant.
Well, I didn't add a constant out here, right? If I added this constant out here, would it converge? No, not the same thing. This one, every time I add a term up to this, I add a 1/5 plus a 1/5. You add infinitely many 1/5s, what do you end up with? Infinity, right? You add 1/5 infinitely many times, you end up with infinity. So that one diverges. But what if I put this? How does this number compare to this number? Which is bigger?
The top one. The top one.
The bottom one is smaller.
The denominator here is bigger, so this one is less than that, right? Well, then if this one converges and this one is smaller than that, what does this one do? It converges. That's the direct comparison test. The direct comparison test idea is figure out a series you already know converges. Compare the one you're looking at to one you already know converges. If it's smaller, it converges. If I knew this one diverged and this one was bigger, I would know this one diverged. So that's the comparison test. Okay, so that's where we're going. The $1 million question will be, here's a series, tell me if it converges or not. Stay off the streets. I'll see you on Tuesday.